Okay, do you see any delay? I think no, right? So, okay. Okay, now let me go from here. Last time we discussed on differentials actually. So differentials means that we have uh, dz, right? We have dz, and oh, wait for a moment. I need to check. Okay, now we have dz, and dz will be depends on dx and dy. Okay, and dx and dy, as we can see from these illustrations, they both are independent. They both are independent, and we are going to look on dz, and if we compare with the real gap, we have some distance, right? We have some difference. Now this difference is sometimes we call the error. Okay, and if you look on the point here, the more closer we are to this point, the difference, okay, the difference between the delta z and dz will be small. It will be closer and getting closer and closer. Okay. Okay. Now, how we can take the these expressions into some applications? Well, if we are looking on some example, like for example, uh, we have dimensions for rectangular boxes, 75, 60, and 40 centimeter. Okay, each measurement is correct within 0.2 centimeter. So we have three measurements: 75, 60, and 40, right? Okay. And we have another measurement, which is 0.2. This is the error, okay, the error. So each one of these 75, 60, and 40, each measurement has error that is around 0.2. So it can be maybe 75.2 or maybe less than 75 minus 0.2. So plus minus 0.2, okay? Now, the question is, it's asking, use differential to estimate largest possible error when volume of the box calculated. Okay, so it's asking, finding the error when we are measuring the volume. Okay, that's the question. I think the question is really direct. So probably we are start with volume is basically we have three sizes, right? We have three variables. So we say maybe x, y, and z. Okay. Now the idea on differentials, we are going to differentiate this volume. So we are going to partially differentiate. Okay. So we will have differentiate with respect to x. This will be equal yz. Differentiate with respect to y. This will be xz. And when differentiate with respect to z, this is xy. Okay, we have three components here. And then when we are partially differentiate this, becomes dv is sorry, dz. Okay, I hope it's clear. I hope it's clear. And then we can write dv as this is yz dx plus xz dy plus xy dz. Okay, now let me copy this. Okay, now I hope nothing wrong with the partial derivatives for each x, y, z. Okay, now we have three variables. Okay, now we are going to calculate dv. Okay, we are going to calculate dv, and we are going to take dv and compare with the volume, the total volume for the real estimate value, and we can find the difference between dv and the volume itself. Okay, now this dx, dy, and dz is actually our measurement for error for each length. So dx, dy, and dz, they are all 0.2 centimeter. Okay? And we are going to input this 0.2 as dx, dy, dz. Okay. Now let's, I'll move to the next page. Okay, I'll go to the next page. So I will write this, let me copy this. So dp will be y is 60, 40, this is 0.2 plus 75, 40, 0.2 plus 75, 60, 0.2. Now if you check the result, this will be 0.2 to 400 plus 4, 3000 plus 6, 4, 500. This will be cancelled. So 4, 540, 4, it's 990, and then 0 multiplied by 2, it's 1980 centimeter cube. Now this is the volume with the error measurements for each length. Okay. Now the volume, the real volume, okay, with the 75 and then 60 and then 40, this is how much is it? 75. It's 118, right? 18, 1888, right? Yeah. Now the percentage, if you want to calculate, this will be multiplied by 100. This will be around 1.1%, or more or less. This is approximate 1.1%, and we can say that this 1.1%, okay, is the error of volume. So the largest possible error for the volume is 1.1%. Okay, so the idea, let me review a little bit on what we have found here, is basically we start by taking this formulations. We need to determine how many variables we have. Okay, how many variables, multi-variables, and then what next is we partially differentiate we make a differentials formula. This is our differentials formula. This part here. Okay. And then after that, we can measure the error. Okay. And it depends on the question whether the question is asking the error or maybe asking the approximations, okay, the value. Okay. All right. Um, maybe questions first. Any questions? Okay, if no, then let me go through. So actually differentials finish. Nothing much for the content, but I think you can also check the uh, the exercise later on. Okay, let's move to the next sections. The next sections is about the chain rule. Okay. Now the chain rule, to begin the chain rule in the partials, I will start with what we have and what we have learned before. That is in the parametric equations, right? In the parametric, right? If you remember, we start doing the parametric from the chain rule of this dy over dt, and we have these definitions, right? We have these definitions, and then we can write the dy over dx as dy over dt over dx over dt, right? Okay. Now in calculus 2 partials, we need to recall that we state z as a function of two variables, x, y. We start with this, and simply we can say also this is a surface, right? And if we if if x is actually function of t, and if y functions t also, then we can write dz as function of xt and yt, right? Okay. Now this means that z will be expressed as a function of t. Okay, because we have x is function of t and y also function of t. So z, ideally, it can be represented as function of t as well, right? So if we take z and we take the uh, differentiate, partial differentiate with the chain rule, then dz over dt will be equal to with this. So if we partially differentiate z with respect to t, this is what we have. Okay, to make sure that what we have here is correct, or we need to confirm, right? We need to confirm. we can also draw a diagram. Okay. So we start from z. We start from z. Z is function of two variables x, y, right? So we can make a branch. This is x, this is y, okay? And then it's each of x and y. Each are functions of single variable t. So this will be, I think, function of t. This is also function of t. Okay. Now from these branches, we can make it. If we want to make z partially differentiate with respect to t, which means that we are going to write z, or we need to derive z with respect to t, then we are going to at least each way we need to fulfill. First, z going to x and going to t. When z is going to x, we can write z dou x. So every time we have a branches, we need to write, instead of d, we need to write the Leibniz notations, this Leibniz notations. We say usually dou z over dou x. And similarly, the y also dou z over dou y. Okay? And then because it's only having one path here from x to t, we have dx dt. And this is dy dt. Now to write this dz dt, then we are going to multiply dou z dou x and dx dt plus this and this, multiply. Okay, that's in practice how we can make sure the chain rule in any variable. Okay, so actually, if you have many variables, okay, can be 2, 3, 4, even 5. In theory, in your writings, it doesn't matter. You still can do as much as you can. Actually, not really restricted to only 2 variables, only 3 variables. You can have more than that. But of course, if you want to translate them into picture or into graphs, it will be a different story. Um, for I think for 3 dimensions, still we can easily draw. Not easy, but still we can draw it. But for 4 dimensions, 5 dimensions, I think that will be a very difficult, because 4 dimensions you need to have more more clear object that separate the dimension in space with the dimension for time. And I think that's difficult to imagine. Yeah. Because 4th dimension we are dealing with time, and in 5th dimensions we are dealing with the multiple space and time. Yeah, and that's, yeah, it's actually like if you read some science fiction story or watching some science fiction movies, that's what we call the parallel universe. But anyway, uh, let me write here for the general rule. If we have w is a function of many variables, x1, x2, x3, and each component for x1, x2, x3, they each are a function of t, single variable t. So we can write this dw dt as dou w dou x1 dx1 dt plus, okay, this is the general general terms in table. Okay. Let me give you more and more example. The example, at least to imagine how we can write the formulations, yeah, for the chain rule. If you have any questions, you can write in the chat box. If you want to take times to take notes when I move and you want to take back to previous one, please let me know. Okay. But I think I will move to the next page. So if you want to take notes, you can take for a little while. Okay, I will move to the next page. Okay, to the next page, let me give you another example. If z is function of xy and x is function of u and v, y also u and v, okay, then what is the chain rule for dou z dou u and dou z dou v? Now we start with the same diagram, z, then it has x, it has y. But from x and y, we have another two u and v, u and v. So if we have dou z dou u, we need to connect z to u. Z, u, z, u. And we have two paths, right? This path and this path. Okay? I hope that's very clear. So we are having dou z dou x, because all having branches, so we are using all with Leibniz notations, and dou x dou u. Okay? And then plus dou z dou y and dou y dou u. I hope this tree diagram can help you to decide how the forms, or what is the forms of the partial derivatives. And then dou z dou v can start with z and then v and z and v, like that. So we can start dou z dou x dou v plus dou z dou y and dou y dou v. Okay, not really a problem, right? I think still you can follow. Let me give you with a real functions. The function has a definition functions. Okay. Let me give you another example. Maybe right here. If w is xy plus yz, y is sine x, and z is e to the x, find the equation for dou y dou x. Yeah, I think I can give you a couple of minutes to try on your own. And the tree diagram is not always perfectly balanced. It depends on the function, of course. Like, well, if you look on what we have here, it's always balanced, like the left and right having the same height, same length. This is also similar, right? Same height, same length. But I think it depends on the functions. Sometimes maybe the left may be longer, or maybe the right longer, okay? Because we have now W is function of three variables. So we have three variables. And then Y and Z, I think they both have single variable X. Right? They are function of X. So if we draw the diagram, we start from W, like W, and X, and then Y, and then Z. Okay? And each Y and Z, they are going to have X. X. I think this is just our diagram. Nothing more, right? According to the information given. So we are starting, first is this. So of course, we start by writing the same and then plus this part, dou y, dou w, dou y, and then dy dx, and then plus dou y, dou z, and then dz dx. And now we are going to evaluate each partials. So first, we evaluate this part. We evaluate with respect to x, which is just y. And then plus this become dou w, dou y become x plus z. And dy over dx will be cos x. And dou w, dou z will be y. And dou z, dou x is just e to the x. Okay, and then we can have all in terms of x. Okay, we can change all into terms x. Y is sine x plus x plus e to the x cosine x plus sine x e to the x. And this will be the results, the solutions. Okay, any questions? we can go to some explanations on implicit differentiations and some other forms that we can also write down. Okay, let me go through here. Okay, let me give you some review on a calculus one on implicit. Although we have learned, I think last week on implicit, but let me just review and take the other forms so that we can have much more um, uh, quite a few formula that we can also use for some solutions. So let's say we have y cubed plus y squared minus 5y minus x squared plus 4. And then the question is finding the dy over dx. Okay. Now, as you remember, to find this dy over dx, in calculus 1, we simply directly derive this with respect to x, right? And then treat y as a function of x. So we will have 3y squared dy over dx and plus 2y dy over dx, right? And 5 dy over dx minus 2x equals 0. And then we are grouping this dy over dx. And then we get dy over dx is equal okay, we get this. Now, if we let this like taking a function, and let f or let y is function of x. Okay. Now doing the same thing with the tree diagram as we mentioned in the chain rule before, we can make this f, okay, and it has x, it has y, and y also have x. Okay. So if we try to make our own chain rule, then this will be equal with plus. Okay. And since this is 0, okay, since this is 0, because we let this is our f, okay, so we can write the d over dx as negative d negative dou f dou x divided by dou f dou y, or we can simply write in terms of minus partial x divided by partial y. Now if we look on what we have here, if we have partial x, we have negative 2x. If we have partial y, we have 3y squared plus 2y minus 5, which is, this is getting the same results. So we can have dy over dx as negative partial x over partial y. This is the function, and it's supposed to be 0, so that's why we have 0 here. Okay, any questions? Okay, let me move to next page. Okay. Okay, now if we have functions, let me give you an example. If we have a function x cubed plus y cubed minus 6xy equals 0. We want to find dy over dx. Now, based on what we have on the previous example, now we can let the f is become this x cubed plus y cubed minus 6xy, and it's equal to 0, right? So we can start by taking this, and then we can have a partial. So partial x, we will have minus 3x squared minus 6y, and then this will be 3y squared minus 6x. Or we have x squared minus 2y and y squared minus 2x. Okay. Now suppose, let's say we have z, that z is our f. We can rewrite the function as z. So z is given implicitly as a function of xy. And then we have the form, and we have the form of another function that has x, y, z equals 0. Okay. Which means this f is x, y, and then function of xy equals 0 for all xy in domain of the function f. Okay, if small f and capital F, they both differentiable functions. So we can differentiate this. So we can differentiate or partially differentiate becomes dou f, dou x, dou x, dou x. Let's say dou x with respect to x. Dou f, dou y, dou x plus dou f, dou z, dou x equal to 0. Well, this is 1, right? And dou y, dou x is 0. And of course, this equation becomes dou f, dou x plus dou f, dou z equals 0. Now, if dou f, dou z is not 0, we can solve dou z, dou x. So dou z, dou x will be negative, or we can write partial of f(x) and partial x and partial z. Or simply we can write partial x, partial z. And similarly, if you want to differentiate with respect to y, similarly we will have, when we write with the light blue, we have this. Oh, sorry, should be y. Yeah, y. And then this is dou z, dou z, dou y, and the same thing. This is 0. Same thing we will have dou z, dou y is partial y, partial z. So if we have 3 variables like this, we can implicitly find the solutions. But actually, it's up to you which method you are using, because basically all methods, they are having the same answer. Let me give you more example. For example, to see how we can apply this formulations. Okay. So we'll give you a little bit time for taking notes if you want to take notes here. If you feel want to ask something, you can write on the chat box. And anyway, for Thursday class, I think you can come for to give. example. Okay, we start on the example, this example. Okay, now I will show you. We have at least two methods to solve this. Okay, I will give you idea for the method that we have just learned. Okay, so first we can let the function of three variables x, y, z. This is becoming our xy squared, x squared plus y squared plus z squared. This is equal 1, right? So we can write the tree diagram in the design that is becoming x, y, and then z having two variables x, y, right? Now we can have dou f dou x, dou f dou y, and dou f dou z dou x, and dou z dou y. Okay. Now we can have this idea of dou f dou x plus um, dou f dou y is we will getting 0, right? So we will have just dou f dou z, and then dou z dou x. Okay, if we want to find the x, okay. So this is equal 0. So dou z dou x will be equal minus partial x partial z, and this will be equal to this is 2x 2z, so will be minus x over z. Okay, and similarly we will get dou z dou y minus partial y partial z. This will be minus y over z. Okay, so this is I will write as first method. Okay, so we are going to use the chain rule, the tree diagram, if you're not sure which you are going to derive, and then take this as your first method. Okay. Now you would like to use the second method, and I believe some of you will try the second method because in most cases it will be more more I think more practice, more practical. So the second way is the one that we have learned, I think way back weeks ago. So we have this, and we differentiate directly. For example, if you differentiate with respect to x, okay, then it means that we are going to have x is our variable, right? Y is our constant. So we treat y as a constant, and z is function of, of x, right? Now we can derive this and become 2x plus 2z the dou z dou x equals to 0. So we'll have dou z dou x is negative x over z. I think much more practical, right? Practical. But if you would like more concise in terms and to see the structure of the chain rule, you can check with this. Okay. So this is the second method. Each method is both are correct. Both are correct. So it's up to you using which method. Same way, if we want to derive with respect to y, this will be 2y plus dou z dou y equals 0. Dou z dou y is negative y over z. Second method. Okay. And that's the end of chain rule 14.5. Okay, any questions? Any question? So whenever you feel probably this first method, whenever you feel maybe you need to take on more details, you can start from the tree diagram. We start from tree diagram, and we start from this f. We start from this f. We're having three variables, okay? And from this z, we have two variables x, y. And now if we start on derivative with respect to x, so we'll have this, and we'll have this, and this, right? That's our choices. So we have this structure. And if we derive with respect to y, we have dou f dou y, and then this dou f dou z multiplied with the, dou z dou y. Okay? Okay. Any questions? No? Okay, if there's no questions, I will just move on to 14.6. 14.6, the directional derivatives. And maybe next Thursday, we're going to have, I think, practice a little bit on chapter 14 in general, including the chain rule and the tangent plane. Okay. Okay, I will move to next slides, next page. So we start with 14.6. The idea is we call the directional derivatives and gradient vector. I think if you learn on learning electric, like I think magnetic fields and other components on this electric, you will see the gradient vector. in physics, right? Can we start by looking at the recall? Okay, recall that z is function of two variables x, y. Can we start with this? First, we already defined in the limit definitions that we have partial x. On x0, y0, we have limit definitions. That is minus divided by h. And partial y divided by h. So we have this two partial x, partial y as in the limit definitions. What's the implications? Okay, what's the implications? As we may learn also from the differentials, that if we have z in this particular functions, so we know that z will depend on x and y. So we can say that this partial y and partial x, this represent rate of change of z, okay, in x and y directions. Okay, let me check whether I have the drawing on. Draw. Okay, suppose we have the directions. Okay, suppose we have the directions. Because we are going to deal with directions, then we are going to have a certain unit vector. Let me just take this. Okay. With the red color. And let's say we have the vector u. And let's say this is the point of x0 and y0. Okay. This vector u is having a component of a and b. So we can say that the vector will have directions. In x unit, it's a, and in y, it's b. Okay. Okay, let's consider this vector u, and then imagine, because this is y, x. Okay. If we have a surface above this xy, the surface of z, now if we are using this unit vector as our directions, then we can simply imagine that the surface can be cut. Let me just show you the picture. There's the picture here. Okay. Now imagine, okay, this is x0, y0, right? If we are going to look on the height of this point, this particular point here, okay, imagine it's the same point here. The point is on the surface, it will be on here. This is our surface. Okay, this is our surface. Now the point defined as point B, okay, if we are going to move this point according to the direction of u, the vector u, it's having x, y directions, right? X and y directions. So let's say this is the direction is this one. So you will see that along the curve or along the surface, the point B will be going to this Q. And let's say this is XYZ. Now, we know that if this P prime and Q prime is the projection of P and Q, then we know that this P prime and Q prime, P prime and Q prime is the factor is equal to some scalar multiplied with the factor U, or we say that this is equal to HA and HB, the directions, or uh, some number H, which is a scalar number. Okay. Therefore, the distance for x and x0, y and y0, we can write here x minus x0 is HA, and y minus y0 is HB. Okay, so x is x0 plus HA, and y is y0 plus HB. Okay, and our delta z, okay, the z minus z0, okay, so z minus z0 divided by h is equal f x0 plus HA and y0 plus HB minus x0 y0 divided by also h. If we take the limit, take limit as h going to be 0. We will obtain the rate of change of z in the direction of u. Okay, so this will take us to definition of the directional derivative. So basically, the directional derivative is the derivative that has certain direction that is usually implies with the unit vector u, usually. So we can write the directional derivative of f at x0, y0 in direction of unit vector, let's say unit vector u, that is having direction of a and b, is we write the directional derivative as d, and with the u means the vector, the directions of f, and then at this point, and we can say this is limit as h goes to 0, f x0 plus ha, y0 plus hb minus f x0, y0 divided by h, provided limit exists. Okay. Okay. Now from this definition, we can further prove that this will relate to our partials, each of our partial derivative, partial x and partial y. So simply, we can write, let me write. Let me write the theorem that if a function differentiable function of x and y, then f has a directional derivative in direction of any unit vector. Let's say u. Then we can have this directional derivative partial x okay. Okay, now this theorem, the last theorem, I will give you a little bit context on why we can have uh, these equations. Okay. Well, let me give you a context. We'll move to the next slide. So if you want to take notes or take a screenshot, you can take a screenshot. Okay, let me go through some context. So if we define a function g, this is a function f that has this definition, and if we define by the definition of derivative at 0, if we have this definition, then we have limit as h going to 0, which is gh minus g0, right? Okay. Or we can write in more clear way that this will be f x0 plus j y0 plus hb minus f x0 y0. Okay. And then this will be equal to our directional derivatives, right? And now we can write this gh in terms of f xy, where x is x0 plus ha and y is y0 plus hb. Okay. If you use the chain rule, this will be dou f dou x, and then dx dh, and then plus dou f dou y, and then dy dh. Yeah, I think you can see the connections now. So this will be equal to the partial x, right? And then this will be a. This is partial y. This is b, right? So we can have g prime h is partial x at xy multiplied by y, partial y, xy multiplied by b. If h is 0, then this will be x0, y0 back to the origin. This is a, and this is x0, y0, b. And we can really see that from these two definitions, this is clearly we can write down the conclusions that the directional derivative is equal okay. And from here, from the directional derivative, I will relate to the gradient factor, which is actually same thing as directional derivative, but different structures. Different structures. Okay, perhaps do you want to have, or you want to take back to the previous slides, or you want to take notes here? I'll go uh, to 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 deal with the gradient factor. So the next section will be the gradient factor. So I will give you these two contexts, the directional derivative, the second is the gradient factor, and then we can have a practice for the whole session, or these two sections. So gradient factor, what is gradient factor? So we first, let me write again, this directional derivative is equal to partial x multiplied by a plus partial y multiplied by b. A and b is the direction of the unit vector for x and y directions. Okay. Now, if you write in terms of vectors, we can write this as vectors of this partial x and partial y, and we are using the dot product for a and b. Okay. And we can write down, and we can rewrite this in terms of the unit vector u, right? Now, these terms, this 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 vector, this is what we call the gradient vector. Okay, so this is the gradient vector. Gradient vector of function f. Sometimes we write in special notations, triangle, but having upside down. We call this gradient vector of f, or gradient of f. Or we can write also del as a del. So we have these definitions. Sometimes we call this del f or gradient of f. So that's the connections. So nothing really fancy, nothing really that having like more complicated definitions. Or we We can also write the delta or the del as or we can write this is with I and j. Okay. Actually the same thing. This is the del f. And remember that this vector u is a unit vector. A unit vector. Okay, maybe giving you more one or two examples if we have time. Okay. Okay, let me give you an example. Find directional derivative of function at point 2, -1. In direction of vector now to solve this, first we can find partial x and then we can find partial y and write the gradient vector. After we write the gradient vector, we need to multiply as a dot product with the unit vector v. Okay. So don't forget to rewrite the factor as unit factor. Usually some mistake will happen. So first, let me write the functions. So write partial x. This will be 2x y cubed. Partial y will be 3 x squared y squared x 4. Okay. So we can write the del f is 2xy cubed plus 3x squared y squared x 4 j. And then at the point 2 and -1, we can write down this is -4 I plus this is 12. 12 minus 4 is 8. 8j. So first we get the gradient factor. And then we find the unit vector. Let's say unit vector is unit vector u. So this will be v divided by the magnitude. So 2 divided by 25 plus 4, so square root of 29 plus 5 square root of 29j. Directional derivative at 2, -1 will be equal to this multiply or dot product with the unit vector u. And this will be negative 4I plus 8j dot product with 2I plus 5j. So this will be negative 8I or negative 8 plus 40 divided by square root of 29. So this will be 32 over square root of 29. Okay, perhaps any questions? Okay, maybe let me give you more sections if we have function of three variables. Okay, if we have three variables. So directional derivative at this point, x0, y0, and z0, let's say three variables, we can write as a limit definitions. The definition is for variables that is more and more is actually still the same context, which we have x0 plus ha, y0 plus hb, and now we have z0 plus hc, and minus f, x0, y0, z0. This is directional derivative of f at x0, y0, z0 in direction of unit vector. Let's say we have unit vector a, b, c. And provided this provided limit is exists. And thus the gradient vector will also have the same structure, but we have now three partials. And still the directional derivative is the gradient vector multiplied with the dot product with the unit vector u. Okay. Okay, I will stop until here, these sections, the directional derivatives and the gradient vectors. We still have a little bit on some additional notes for the tangent plane in our case in the gradient factor, and how to maximize the gradient factor. And I think that part we will finish on Thursday. So I will just stop here. And is there any question? I will show you the attendance sheet, and then I will have a feedback for today's, okay, a feedback for at least chapter 14, the first part on chapter 14. Okay, I will stop this sharing. I will stop the sharing, and I will show you the okay. So please scan the QR code. If you have, then you can start to play our game. So please scan the Mentimeter code. If you haven't scanned the attendance, let me know. I will show you later after we finish the game. Okay, please join the game to see the feedbacks. And I hope the time is enough. Okay, let me go through. Okay, let's start. 3, 2, 1. Okay, I hope you still remember how to find the limit. And I hope the time is enough. Okay, let's see. Okay, yeah, it doesn't exist. So you need to check x equal 1, y equal 1, and then y equal x. You can also check with that one. Okay, so let's go. Okay, Booty, make both face. Yeah, I hope you can change your name so I know which one. Okay, good. Get ready for the second question. Okay, let's start. 3, 2, 1. Okay, find the partial derivative at that point, at that 0, 1. I needed to type in the answer, the number. Type in the number. Okay, 22, 21, 20. Okay, I think most of you did a good job. Okay, right, good job. Okay, last question. Get ready, 3, 2, 1. So you need to find the tangent plane, especially you need to make it into z equal ax plus by minus c, and you need to define um, the answer. Okay, I think maybe I will check whether I write the right question. It should be plus c, right? So it should be minus 1. Okay. Anyway, okay, let's see. Okay, so congratulations, you win the game. So this will be the end of our lecture. Um, I will prepare more uh, feedbacks in the future, maybe next week. But perhaps we will have quiz. Okay, we will have quiz chapter 12 and 13, maybe on uh, not this Thursday, but maybe next week. Next week Thursday, I will announce on the Moodle. Okay, so I think we'll have uh, next meeting on Thursday for continuing the chapter 14. And I think for the last section of chapter 14, I will add in the additional videos alongside with some examples and review to help you more to understand chapter 14. Okay, so I think that's it for today. So thank you for joining the class, and sorry for the late class because of the technical difficulty at the beginning.